If you don't mind, please let me take a selfie first. Say cheers. Thank you very much. OK, so hello, everyone. Today, I want to show you how to build a functioning debugger in just 200 lines. I guess the number when coming out with a title, but the final result is actually smaller, which is always a good thing. And let me start by introducing myself first. My name is Stan Stando, and I'm from Taiwan, but now I live in the UK. And I'm a developer at Shopify's Ruby Developer Experience team. And one of our major projects is the Ruby LSP, which just became VS Code's default option for Ruby users last month. And if you are interested in language servers, my teammate Vinit will be giving the talk about it tomorrow. And my another teammate, Alex, will also talk about like RBS with RBI and service comparison tomorrow too. So please check out their talks if you are interested in these topics. And I also maintain projects like IRB, Reline, and Century Ruby. And finally, you can find me on these platforms with these IDs. So last year, I gave a talk about how to use Ruby Debug to boost your productivity. And originally, I wanted to give a similar talk with more advanced debugging techniques. But after doing a debugger workshop with my team, I found that learning by building also applies to debugging skills. So in this talk, I want to help you get familiar with debuggers by looking inside it. I know to many people, debuggers are like mysterious black boxes and potentially very hard to approach. And I want to change this mindset through my talk. And secondly, by learning to build a debugger, we can gain insights into its capabilities and potential limitations, which will guide us in knowing when to use and how to use a debugger effectively. And also using the tools and techniques I'll be presenting, which we typically don't encounter when building applications, you will be able to build custom tools for yourself or your team. And we will be building this debugger in 5 steps. In each step, I will explain why we want this feature with a demo, and then I will highlight the important parts of the implementation. In other words, I won't explain things line by line. But also don't worry if you are curious about the details. I will show you the code repository at the end of my talk, so you can take your own time to go through it. But before we start visiting the first step, I want to first introduce a few key concepts and tools that we will use for this debugger. They are binding objects, tracepoint class, and the Reline library. Oops. So let's talk about binding first. According to its document, binding objects encapsulate the execution context of a specific part of the code and retains this context for later use. This means if you get a binding object, you have access to the context it captures. We can understand it better by looking at this example. If we call binding at the top level, like this, and call self on it, it just returns main, just like if we call self directly. But let's see what happens if we get a full instances binding through the getBinding method. So if we call self on it now, it returns the full instance. And then we can also access the full instance's internal state. But most importantly, we don't just get the context of the full instance, but specifically the context in its getBinding method. So for example, we can see the method argument's value. And finally, a binding object also holds the location of the context it captures. And having the ability to access this information is very important to build a functioning debugger. But how can we get a binding object without changing our program to return it? This is when we need a tracepoint class. Tracepoint allows us to trace different types of Ruby execution events. And you can think of that as Ruby level callback events. And for example, there is a raise event that will be triggered whenever an exception is raised. It also has events like call or return. But to our mini debugger, we only use its line event, which provides information like line number, file path, and most importantly, the binding object of that execution context. Here's an example code of it. When the greeting method is run, the trace point block will be triggered. And when the put inside greeting is run, the trace point block will be triggered again. So this script will print the following output. And in the second trace, you can see we also have access to the binding through trace point. And if this is the first time you heard or want to use trace point, I want to give you some heads up. Because even though it's very convenient, having a trace point running with your program could add overhead to it. And sometimes it could affect its performance by a lot. And also, having trace point running makes optimization difficult. And most trace point events actually cancels out YG's optimization. So the general recommendation is don't use it in production. And let's move on to the last key component, readline. It's a powerful library that handles terminal input, and it powers IRB and Ruby debug. In addition to reading input from the terminal, it also provides advanced features like auto-completion, multi-line input, and input history. However, we won't be using any advanced features today. The usage is very simple. We usually use it with a while loop, which waits readline to capture the input, and then we handle the input and wait for the next iteration. If we run the example, it looks like this. OK, now I think we have learned all the tools we need to know. Let's start building the debugger. So in the first step, we'll implement the breakpoint method called binding.debug and the minimum REPL, which will be similar to when you use binding.pry or binding.irb. And in the second and third steps, we will implement state debugging through the step and next command. And fourth step, we will add breakpoint commands. And finally, we will add the debugger executable. And this is the script I will use to demonstrate debugger's features. It's a simple Fibonacci implementation that I hope doesn't have any bug, actually. So in the first step, we want to implement a basic breakpoint and a minimum REPL. To be more specific, we want the program to stop when it hits the binding.debug breakpoint, similar to what happens when we hit binding.pry or IRB. And once the program stops, the debugger will open up the REPL, which will read the input, evaluate it, and then print the result. And finally, we want to have commands to either continue or exit the program. So after this step, our program will look like this when we need to debug it. We first require the debugger, and then we place binding.debug in the place we want to investigate. Let's see a short demo of it. As you can see, we can stop at a breakpoint, see the nearby code, and then have access to the breakpoint's context, like the method argument. And if we continue, it will then hit another breakpoint because we are inside a recursive method. So we can also exit the program. And to achieve what I just demonstrated, it actually only requires 60 lines of code, which is pretty impressive in my opinion. And now let me break it down into smaller pieces. So let me start from the bottom of the file, which looks like this. We initialize the session instance and store it in the session constant. This is because we only need one debugger session at a time, and we can access it through the constant. I will talk about the session class in details just a moment. And then we add a debug method to the binding class. Have you ever wondered why breakpoints often start with binding? This is because by defining a method on the binding class, it allows us to pass the binding itself very easily. And in this case, we pass the binding to the debugger session suspend method. So what does the suspend method do? We already know it takes a binding object, and then there's a while loop that's pretty similar to our readline example. But in this case, we handle continue and exit commands. And to continue the program, we actually just break the loop. And to exit, we call the exit method. And at the bottom, we can see there's an eval input method that evaluates the input with the given binding. And finally, we need to display the code around the breakpoint, like the picture on the right. And it's not the main focus of this step, so I will just quickly go through it. This method also takes a binding, which we use to get the file path and line number. And then with the information, we calculate and display the start line, end line, and file name. And then we iterate through the lines that are covered in the range. So with these 3 small steps, we have implemented a basic REPL-based debugging tool. Now let's move on to the second step. Let's add some debugger features to it, like step debugging. And let's start with step in, which allows users to step to the next program execution. And to better demonstrate this feature, let's move the breakpoint outside the fifth method so we can step into the method. And here's a demo. So now you can see we are at the beginning of line 12. And then if we type step, we can step into the fifth method call and have access of the variables, just like as if we put binding.debug inside the method directly. And to implement this feature, we first need to handle the step command in our REPL loop. And then we need a step-in method. And once we code it, we let the program continue. And now let's take a closer look at the step-in method. So once the program continues, like let's say from line 12, it waits the next execution, which is the if condition, and then the trace point will be triggered. However, trace point itself cannot tell if the execution are from the program, from the debugger itself, or it's from standard libraries, or Ruby internal, or it's actually the user's program. So we need to teach the debugger to only stop at the user's program. And we can identify those internal events by comparing the trace point events path with certain pattern. And we can skip the block execution with the next keyword if the path matches the pattern we want to skip. And if it's not an internal execution, we want to first disable the trace point so it doesn't interfere with later executions. And then we call the suspend method with the current events binding. Now we have implemented the debugger step-in functionality. However, when we debug a program, we usually don't need to see every single execution. So being able to skip some of them will be very helpful. And that's why we need to implement step over. In this step, we don't change our program file. However, we will try to skip line 12 and only step into line 13, which will look like this. Now we stop at line 12, but instead of typing step and step into it, we type next and move directly to line 13. And then we step into line 13. And the implementation of the next command is actually pretty similar to the step command. First, we need the case for the input, and then we implement step over, and finally we break the loop. If we compare step over with step in, the main difference is that step over also skips when the line's call stack is deeper than the current stack. In most cases, it means stepping to the next line. And it's not super easy to understand, so let's add some puts to visualize it. So when step over is called, we print the current stack's depth, and every time the line is executed, we also print the line's content and its depth. And after we run the program again, this is what we will see when we step over line 12 to line 13. If we zoom in, we can see that there are around like 50 entries, and each entry represents an execution that need to be skipped through the step command. So we actually skip 50 steps with the next command. And this is why this feature is called step over, because we step over these executions. And with the step over feature, now our mini debugger is able to perform basic step debugging. But even if we are able to step over to the next line, our mobility inside the program is still very limited. And ideally, we should be able to dynamically to stop at the location we want to just by using a breakpoint. And for example, break in a jam without bundle open. So in this step, we are going to introduce break command to help us achieve that. And with the ability to add breakpoints through the break command, we also want to be able to list all the breakpoints we have added and then delete them when necessary. So with the breakpoint commands, we don't have to place binding.debug close to the code we are investigating anymore. So for demonstration purpose, I'm now moving binding.debug to the very top of the program. As you can see, now we will stop at line 2. But by using break command, we can add a breakpoint at line 8. And once we continue, it will stop at line 8 as if we put the binding.debug there. And we can also have multiple breakpoints and list them with using break command as well, when just now with arguments. And finally, we can delete any breakpoints if we want to. So to implement this, first we need a way to check breakpoints. So we initialize an array in the session for that. And then we need a helper to add breakpoints, which initializes the breakpoint, add it to the breakpoints list, notify users that the breakpoint has been added, and then enable the breakpoints trace point. And in this step, we need a bit more change on our REPL as well. So first, we now need to split our input because now our command can take an argument. And then we use regular expression to handle the breakpoints addition through the break command. Finally, if there is no argument provided, we just list all the breakpoints. And the delete command is actually very simple as well. We take the ID as argument and use it to locate and delete the breakpoints from our breakpoints list. And now comes the important part of the step. We need to implement the breakpoint. But the implementation is actually rather simple. Here we just use tracepoints line event to check if the execution happens at the location of the breakpoint. And if it is, we suspend the program with the tracepoints binding. But as you may have noticed, such line-by-line comparison could add a lot of overhead to performance, and especially when debugging any real-world application. And you are right, so this is not how RubyDebug implements its line breakpoint. However, I also couldn't replicate its implementation because, because it's a lot more complicated. So roughly speaking, it collects ISIG objects from object space, and then it locates the ISIG object of the breakpoint location. And then it uses heuristic to check which is the best line to stop. And finally, it activates the tracepoint on that ISIG object's specific line. So in other words, it reduces runtime overhead with a more complicated but sophisticated breakpoint activation logic. And the implementation requires more than 100 lines of Ruby code and around 80 lines of C extension. So I chose not to implement it here. And I want to thank Koichi Sasada to help me understand this part of the logic. So now we have a functioning debugger that works pretty well for our case. However, if we look at the program, there's still something to improve. Even though we don't have to change the program to add breakpoints anymore, we still need to update it to require the debugger, and then add the first breakpoint at the very beginning. So in the last step, maybe we can also make those two changes redundant. And after this step, we want our example program to look like this. No debugger-related code at all. So now we will use this newly added execdebug executable to run our program instead of just running Ruby. As you can see, it will stop at the very beginning of the program execution and allow us to add breakpoints through the breakpoint commands we added from last step. So how does it actually work? If we look at the debug executable, it's also just a Ruby script. But in this script, it calls kernel.exec to replace the current process with another Ruby process, which roughly looks like this. It tells Ruby where to find the debugger file and require it, and through the Ruby opt environment variable, and then execute app the RB as usual with the debugger required. And in the debugger, we need to check if it's required through the executable. If it is, we stop at the beginning of the program. So here we have finished our debugger. And the result only takes 189 lines. And to recap, by using reline and binding, we are able to implement the binding.debug breakpoint and the working REPL. And with tracepoint, we implemented basic step debugging that allows us to move with a close proximity of the binding.debug breakpoint. And finally, by having breakpoint commands and the debugger executable, we are able to debug a program without modifying it at all. Now that we know how a debugger works, I would like to talk about how to choose our debugging tools. So please bear with me with this oversimplified graph for abstraction levels. So at the bottom, we will have CRuby, and then standard libraries, and gens, and at the top is our Ruby program, like Rails apps, for example. And if you still remember, when we implemented stepping, we skipped these executions. This is true to most Ruby debuggers, like Ruby debug or Writebug. So that means we can't probably debug these components with a Ruby debugger. And we also know that debuggers can run tracepoint events and store additional information in addition to what your program does. And although we didn't implement it today, debuggers often stop or resume threads without you knowing it as well. So if your project falls in the standard library and CRuby range, debuggers, Ruby debuggers probably won't work well on it because of the side effects and also because the executions it filters out. But for CRuby developers, they can grab lower level debuggers like GDB or LLDB because they need to focus on a different level of details. And for IRB development, I actually mostly use puts to reduce variables in a runtime environment. However, for most people sitting in the room, your project probably sits at the top layer. If that's the case, feature-rich Ruby debuggers should work well for you. And if you are not sure why, please watch my talk from last year's RubyKaigi. And it's why I usually use RubyDebug when I'm working on RubyLSP, for example. And I hope this can clarify some confusion around debuggers' helpfulness. Because using debugger or not depends on context, not individuals' belief. So you can be a puts debugger when you need it to, but when you can use a more powerful debugger, you shouldn't avoid it either. So as promised, here's a REPL for the entire debugger project. And I try to split all the steps into individual commits. So if you go through it commit by commit, it should be very clear on how the debugger is constructed. And finally, if you want to add some follow-up features to the debugger, here are some ideas. First is that you can make step and next command to accept an integer argument. For example, step 2 means step twice. Or you can implement a catch command, which will add a breakpoint that will be triggered when an exception is raised. You can use tracepoint's raise event for this. And finally, you can implement a finish command, which will finish the current frame. This is also another commonly used step debugging command. And that's all for my talk. Thanks for listening.